Okay, in guide sheet number 7, we're going to be dealing with the conservation of momentum. Now, these are energy and momentum. We call them the conservation laws. They're two of the big concepts in Newtonian physics. Energy is conserved, stays the same in a system, and then momentum in collisions stays the same. Now, in this case, in momentum, it's a little bit more complicated in that momentum doesn't always stay the same in a system. It depends on where the forces are coming from. In order to figure that out, we're going to look at this in terms of the third law of motion. For every action force, there is an equal and opposite reaction force. Okay, so in a collision between two objects, object 1 and object 2, the force between them must be equal in size and opposite in direction. Keep in mind the plus a little logic section. The forces of these two objects experience must occur for the same amount of time. Okay, so the forces can't be happening if the objects aren't in contact. There's no way for one object to stop touching the other object and still have this force acting. So as long as they are in contact, there will be these forces. Those forces will exist for the same amount of time for each object, 1 and 2, A and B, whatever you want to call them. Now, that leads us to the forces being equal but opposite, the times being equal. Now, that leads us logically to say, well, if the times are equal and the forces are equal but opposite in direction, then the force applied by 1 times its time that it stays on is equal to the opposite, F2, times the time that it stays on. Now, those are impulses. Now, what that says to us is that whatever impulse, and therefore whatever change of momentum is created by the first object, will be the same as the impulse, and thus the change of momentum created by the second object, but it will be opposite in direction. Now, the opposite direction is important because momentum is a vector quantity. What this indicates is that in any collision where the forces are internal or between the objects, then the momentum gained by one object will be equal to the momentum lost by another object, or their total change of momentum will be 0. They will stay the same. Now, that does not mean that each individual object keeps the same momentum. It means that all of the objects in the system, when we add up all of their momentum, all of their momenta as the plural, it will be the same as it was before the collision. And we say collision, but a collision could be an internal explosion. It could be springs released between two objects. So the word collision doesn't mean the two are coming in and hitting each other. It means there's some kind of internal force between the objects. Okay, so let's try to take a look at that in some various situations. Got a club head with a mass of 0.17 kilograms hitting a golf ball, which is only 0.046, a lot less mass. Which object experiences the greatest force? Again, this is a situation where they must be the same. The third law, a law of physics, says that the forces must be equal. Since the time period they're going to be acted upon is the same and the forces are the same, then the impulse both are undergoing are the same. Which object experiences the greatest change in momentum? Well, momentum is equal to the change of impulse. So if the impulse are equal to the impulse. So if the impulses are the same, then the change in momentum for each must both be the same. Now, it's in this final part where we start to see the differences. The golf club has much more mass. Therefore, it will suffer or undergo less acceleration because, according to the second law of motion, the acceleration of an object is inversely related to its mass. So in terms of which one will suffer the greatest acceleration, it will be the thing with less mass, so it will be the golf ball. So we would see some slowing in the golf club when it hit the golf ball. what that would do is transfer momentum to the golf ball, and it would start to move, and it would move at a much greater velocity because of its small mass than the club head was. Okay, so here's two equal mass objects, a cue ball and an 8-ball. They hit each other. Now, just because the mass is the same doesn't change a whole lot. The greatest force has to be the same. Impulse has to be the same. Change in momentum has to be the same. One thing here that's different from our first case is they will both experience the same acceleration, but only because they have the same mass. Okay. If they have the same change in momentum and they have the same mass, then they'll have the same acceleration, only because they have the same mass. Okay, large truck and a Volkswagen Beetle, which we assume to have much less mass. Which object experiences greater force? Again, they must both be the same. There's no choice here. The third law of motion, a scientific law, which is something that humans have never been able to break, says it must be the same. Which object experiences the greatest impulse? Force is on for the same amount of time. The force is the same. Impulse is the same. Momentum is equal to the change of is equal to the impulse. The change of momentum is equal to the impulse. Therefore, it must both be the same. Now here, experiences the greater acceleration. Assuming the VW has less mass, the VW will suffer the greater acceleration. It will gain more velocity because it has less mass. If we take the same argument to a cannon and a cannonball, now this is a case where you'd say, well, this isn't really a collision. The cannonball is being shot out of the cannon. But the reason it's going to leave the cannon is that there is this collision force of explosion inside the barrel. The pressure is going to push equally on the cannonball and on the cannon itself. So the forces between them must again both be the same. The time duration is going to be while it's in the barrel. As soon as it leaves the barrel, the forces will go away. Therefore, the impulse must also be the same. The momentum change must be the same. The velocity change will be greater for the thing with less mass, the cannonball, and the acceleration will be greater for the thing with less mass, the cannonball. So we'll see the cannonball come out of the barrel very fast, but at the same time we'll see the cannon recoil backwards against the direction of the cannonball, but it'll recoil much slower because it has a lot more mass. So recoil, if you've ever shot a gun or some other device that has enough outward projection that forces the projector to come back at you, you've experienced this law of conservation of momentum in action. Recoil is a direct result of the impulse from the internal forces being equal on both objects. Okay, so we're going to try to apply that to some few other situations and talk more importantly about the vector nature of momentum in our next episode.